Welcome, friends. The narrator is glad that quiet company gathers again for a soft journey. Whether someone drifts toward the edge of sleep or simply rests after a long day, a calm place opens here. Somewhere in the world a blanket settles, a lamp glows faintly, or a window reflects the night. A moment of stillness rests across that space, steady and gentle. In that stillness, the narrator moves into the subject at hand, a solitary comet once seen in Earth's sky, and then lost again, a visitor whose path crosses the inner system only briefly before fading back into space. From this point, the story flows without division, resting in the present tense of motion through the solar system. A comet appears in the sky as a faint blur, perhaps little more than a smudge of light against a background of steady stars. It is an object composed of dust, ice and rock, formed billions of years ago when the solar system was young. Comets belong to reservoirs far beyond the planets where sunlight arrives weekly and where temperatures remain cold enough that volatiles stay frozen for geological spans. When one of these bodies wanders inward, it carries with it a record of early solar system materials. Only a few grains of dust and ices reveal themselves to observers, and the rest remains hidden in the darkness of space. The phantom comet at the centre of this narrative is one of these wanderers. It appears once in historical observation, noted in records and measurements, but never again. Its single appearance joins a long list of transient objects, each of which leaves only a small trace. A scientifically accepted fact holds that many comets are long-period or even dynamically new bodies, entering the inner system for the first time after billions of years in distant reservoirs. The phantom comet fits within this category. Its motion through the sky, as reconstructed from fragmentary observations, suggests only that it passed close enough to Earth's line of sight to be seen. After that, its path simply becomes too uncertain to follow. A poetic detail settles quietly into this scene. Even a faint comet glows more brightly than any of the grains that make it, and the glow itself is not the comet's own light. Sunlight reflects off tiny particles, each one no larger than fragments found on Earth's windswept beaches. The tail that stretches outward does not glow from heat, but from reflected irradiance scattered in tenuous gas. In that faint radiance, one can almost imagine how observers once searched the sky for such visitors looking for changes against familiar constellations. A scientific mystery remains unresolved. With only one recorded apparition, no one can confidently state the comet's origin or its true orbit. Without multiple observations spanning days or weeks, calculations cannot lock onto a stable solution. The orbit could be long-period returning after tens of thousands or millions of years, or it could be open, carrying the comet out of the solar system entirely after only one pass through the inner system. Both outcomes are compatible with the limited data. The uncertainty itself becomes part of the object's legacy, leaving questions that recur whenever astronomers revisit these old sightings. Soft ironies move within this narrative. It takes billions of years for a comet to form in the early solar system, yet its visible life near the sun may last only days. It takes only a moment for a human observer to record a sighting, yet the object's path may extend across the diameter of the solar system. It takes only thin sunlight to illuminate a tail stretching millions of kilometers, yet that same light reveals almost nothing about the nucleus at the center. These observations settle into the broader rhythm of celestial motion, in which long processes and brief appearances coexist. The comet persists as an analogy to a quiet exhale from the outer darkness of the solar system. A body that spends nearly all of its existence in deep cold, drifting among ancient debris, can pass inward, once brighten for a short time and vanish again. The inner system responds only with a transient glow, and then the sky returns to its usual stillness. In this slow shifting of position and brightness, the phantom comet becomes part of the larger continuous pattern of icy visitors entering and leaving. Against this backdrop, the narrative approaches the next region of exploration, the distant zones where such bodies form and where they remain undisturbed until gentle forces set them on long inward journeys. The comet, glimpsed once and never again, begins its story in a region where sunlight hardly reaches, a region defined less by motion and more by stillness. That region awaits in the deep cold beyond the planets, where ice and dust collect and endure across deep time, far from the warmth of the sun, beyond the orbits of the giant planets, and beyond even the scattered icy bodies that drift near their gravitational influence. The deep cold of the outer solar system rests in near-perfect stillness. In this region, sunlight weakens until it becomes little more than a distant glow, unable to warm surfaces or disturb frozen chemicals. Here, in temperatures only a few tens of degrees above absolute zero water, ice carbon, dioxide, ice carbon, monoxide, ice, and more complex volatiles remain solid across spans of time that stretch from the formation of the solar system to the present day. This is the environment from which comets draw their nature, dark, fragile, and ancient, carrying the preserved chemistry of an early epoch. Comet nuclei form in these outer zones when small grains of dust collide and stick together, sheltered from energetic radiation by the sheer distance from the Sun. A scientifically accepted process states that icy material accumulates gently over millions of years in the protoplanetary disk, creating porous, loosely bound aggregates. With each collision, particles grow, merge, or fragment, and those that remain intact increase in mass until they become kilometre-scale objects. Even at such size, their gravity is weak and their structures remain fragile. They hold within them mixtures of dust and ices layered in irregular patterns, shaped more by chance than by orderly composition. One lesser-known poetic detail arises from this region. Sunlight reflected from these icy bodies is so faint that their albedo, their reflectivity, hardly matters. Some are covered in dark organic compounds, formed by cosmic radiation over billions of years, giving them a charcoal-like surface. Others retain bright patches of cleaner ice. Yet from Earth's perspective, both bright and dark bodies appear equally invisible, unless they venture close to the Sun. In the deep cold surfaces do not shimmer or glint. They stay as quiet as the vacuum around them. A scientific mystery endures concerning how many such bodies remain in these distant reservoirs, and how often they drift inward. The number of objects beyond observable distances cannot be counted directly. Astronomers infer their presence from indirect gravitational effects and from models of the early solar system, but large uncertainties persist. Some bodies may be leftovers from the earliest planet-building processes. Others may have been flung outward by the giant planets. The phantom comet, glimpsed only once, fits naturally into this uncertainty. It could have belonged to a vast population that rarely betrays its presence. Soft ironies settle through this icy domain. It takes only a small amount of heat to vaporize the surface of these bodies, yet they spend almost all their existence far from any source of warmth. It takes billions of years for a nucleus to form, yet only a brief sweep near the Sun to reshape or erase it. It takes countless collisions to build these fragile structures, yet a single close passage to a planet can scatter them into new orbits. These slow and fast motions coexist across scales in a system that rarely hurries. A modern analogy arises gently. A comet resting in this remote region resembles a grain of frost sitting in the shade of a vast winter forest, unseen, untouched, and unchanged, until some shift in the environment loosens it from its resting place. When it finally moves, it does so without intention or urgency, driven only by forces that have acted since the beginning of the solar system. This outer region serves as the farthest frontier in the story of the phantom comet. Before it glows near the Sun, it spends nearly all its existence in this deep cold, drifting among countless other icy remnants. Only when something disturbs the quiet, such as a gravitational nudge from a passing star, or a gentle tidal force from the Milky Way, does its long inward journey begin. That gradual shift, barely noticeable over millions of years, forms the next step in the comet's path, and the narratives move toward a realm where faint motion replaces stillness. Far beyond the realm of the planets, the solar system extends into a region so sparse and so cold that it is defined more by what cannot be seen than by what can. This distant zone, known as the Oort cloud, surrounds the Sun not as a solid shell, but as a diffuse sphere of icy remnants stretching tens of thousands of astronomical units in every direction. In this space, individual objects drift with such separation that each one may remain alone for the entire age of the solar system, never colliding, never warming, only circling the sun in slow, elongated paths. The Oort cloud exists as a theoretical construct supported by strong scientific consensus, its presence inferred from the behaviour of long-period comets, whose trajectories suggest origins far beyond the outermost planets. No telescope has ever imaged it directly. Its vastness is observed only through the rare visitors it sends inward. A scientifically accepted fact describes its formation. Early in solar system history, as the giant planets grew, their gravity scattered countless icy planetesimals outward. Some escaped the sun entirely flung into interstellar space. Others slowed just enough to remain bound, settling into distant elliptical orbits. Over time, passing stars and galactic tides reshaped these orbits into a nearly spherical distribution. What remains today is a cloud of ancient bodies moving slowly through the outskirts of the sun's gravitational influence. The phantom comet belongs naturally to this population, a fragment of early solar system material stored in deep cold before drifting toward the inner realms. A quiet poetic detail resides in this region. Each object in the Oort cloud experiences night without sunrise. Although the sun dominates their orbits, its light is so faint at such distances that it resembles only the brightest star in a black sky. Shadows form without meaning. Surfaces remain unchanged for billions of years. Even cosmic rays passing through leave only shallow imprints. Here time spreads out like a frozen plain, and nothing stirs except the slow, gravitational tides that act across enormous spans. Yet a scientific mystery persists. The exact population distribution and boundaries of the Oort cloud remain uncertain. Researchers estimate its size and mass using the orbits of comets observed near Earth, but no direct measurement exists. The number of bodies may range from trillions to far more. The phantom comet fits naturally into this ambiguity, a representative of a population too distant and too faint to count. Its singular appearance hints at many others that never approach the sun, remaining permanently hidden in the outer dark. Soft ironies echo through this region. It takes the entire history of the solar system to build such a vast cloud, yet each individual object within it may complete only a few orbits around the sun in all that time. It takes only the faintest gravitational tug from a passing star to alter an orbit, yet that same orbit remains otherwise unchanged for millions of years. It takes only a brief appearance near the sun to reveal a comet's presence, yet the journey from the Oort cloud to the inner system occupies more time than all of recorded human history. These contrasts rest gently in the quiet of deep space. A modern analogy helps frame this remoteness. The Oort cloud resembles a distant silent reservoir whose waters are frozen, but not static, slowly shifting under wide imperceptible tides. Nothing moves quickly, yet everything drifts gradually. It is not a structure built by the sun, but one sculpted by time and gravity on scales that exceed ordinary comprehension. Within this slow and delicate architecture, the phantom comet begins its long path inward. A small shift in its orbit, perhaps caused by a distant stellar passage or by the overall gravitational field of the Milky Way, nudges it toward a trajectory that will eventually intersect the planetary region. This nudge marks the first step in a fall that may last millions of years. The comet's journey does not begin with motion, but with the slightest imbalance, a gentle push that tilts its orbit into a new shape. From that moment its path curves inward, beginning a descent toward the sun that mirrors countless others before it. As the narrative moves with the comet, the outer boundary of stillness gives way to slow inward motion. The next region lies where gravitational shifts accumulate over vast intervals, gradually transforming a distant silent object into a traveller, bound for the warming inner system. In the distant outskirts of the solar system, where the Oort cloud drifts in near-perfect silence, small gravitational influences accumulate with remarkable patience. A passing star moves many trillions of kilometres away far enough that its light reaches these icy bodies only as a faint point, yet its gravity leaves a measurable imprint. The Milky Way itself contributes a large-scale tidal field that tugs gently on the cloud, lifting and lowering the orbits of its countless inhabitants over intervals measured in millions of years. These forces remain weak, but the orbits they shape are equally fragile. A slight shift in inclination or eccentricity can redirect a distant body's long, elliptical path, so that after an immense span of time it begins a gradual fall toward the inner solar system. This process is accepted scientifically. Perturbations from passing stars and the galactic tide are sufficient to dislodge weakly bound bodies, sending them inward as long-period comets. As one of these bodies is nudged from equilibrium, nothing about it changes immediately. Its surface remains dark. Its rotation stays slow and irregular. Its temperatures remain at levels where nothing sublimes, nothing melts, and nothing moves across the nucleus. Only its orbit begins to shift, stretching into a new shape that will in time bring it closer to the Sun. The object does not accelerate rapidly. Instead, it drifts along its altered path with patience built into the fabric of celestial mechanics. Millions of years may pass between the moment the shift begins and the moment the body reaches the planetary realm. The phantom comet's journey fits this timeline, a long descent, initiated by forces too distant to observe directly. A poetic detail emerges in this deep realm. Tiny cometary bodies, though invisible from Earth at these distances, are illuminated softly by the Milky Way. Starlight, faint and diffuse, falls upon their surfaces without warming them. This light carries the imprint of countless stars spread over the galactic disk, bathing the icy bodies in a glow far too faint to reveal texture or colour. Were someone to sit upon the surface of such a nucleus, though no such presence exists, the galaxy would stretch across the sky brighter than the Sun itself, but many times more distant and cold. Even as the comet's orbit begins its inward curve, a scientific mystery lingers. Researchers can model how the galactic tide acts upon distant bodies, and they can calculate how often passing stars perturb the cloud, but they cannot determine which specific star triggered any single comet's journey. The histories of most long-period comets remain inaccessible. Only their observed paths near the Sun hint at possible origins. For the phantom comet, with only one sighting recorded, no such reconstruction is possible. Its entire inward fall, spanning perhaps millions of years, leaves no trace except the brief moment it became visible to observers. Soft ironies weave through this stage of the journey. It takes only a distant star's barely perceptible gravitational pull to redirect a comet that has rested in place for billions of years. It takes only a slight change in orbital energy to shift the future position of a nucleus by billions of kilometers. It takes only the faintest cosmic influence to send a body hurtling toward the Sun after an age of stillness, yet the journey itself unfolds at a pace slower than any human measure of time. These contrasts reflect the quiet interplay between vast forces and small objects in the outer solar system. A gentle analogy comes to mind. The perturbation resembles a soft ripple moving through a frozen lake. The ice itself does not crack or melt, yet the ripple travels, passing through every part of the surface, altering positions so subtly that the change is detectable only after great distance. The comet's orbital shift is similar a ripple in its trajectory that becomes meaningful only after many revolutions through the outer dark. As the comet's orbit slowly shrinks, the influence of the Sun becomes marginally stronger. At first, the increase is so small that the comet remains unaware of any warming influence. Temperatures stay nearly unchanged. The object continues its drift with neither luminous tail nor coma indistinguishable from any other piece of rock and ice in the vast cloud. But gravitational acceleration is patient. With each passing millennium, the comet's speed increases fractionally. Its distance from the Sun decreases by increments too small to measure across a single lifetime. Eventually, across geological time, it descends far enough inward that sunlight grows brighter, though still faint compared with what planets receive. At thousands of astronomical units from the Sun, the nucleus begins to experience just enough thermal input that the outermost layers may undergo subtle restructuring. Molecules trapped within the ices shift positions. Volatile compounds such as carbon monoxide or nitrogen might begin to rearrange or migrate on microscopic scales. These changes remain dormant too weak to create visible activity, yet they foreshadow the transformation that will occur as the comet continues its approach. For the phantom comet, this transition marks the beginning of departure from the outer domain and movement toward a region where solar radiation begins to play a more significant role. Another quiet scientific uncertainty lies here: how exactly the structure of a cometary nucleus evolves during this long inward drift. Laboratory studies, spacecraft missions, and comet encounters have revealed that nuclei can contain mixtures of dust and ices in complex porous arrangements. However, the internal behavior of these materials under extremely cold conditions over enormous timescales remains only partly understood. The rate at which volatiles migrate the strength of the internal matrix and the patterns of subsurface stratification are all subjects of ongoing research. This uncertainty folds gently into the phantom comet story, since its entire internal evolution remains unknown. Soft ironies arise again. It takes billions of years for a nucleus to store volatiles, yet only a few thousand years near the Sun to release them. It takes the entire history of the galaxy to shape the comet's initial orbit, yet only a minor nudge to begin its inward journey. It takes only one appearance near Earth to record its presence, yet countless centuries of travel to bring it to that single moment. These ironies drift like quiet echoes through the long arc of the comet's path. Gradually the Sun becomes more than a distant star. At hundreds of astronomical units, its warmth starts to lift ultra-volatile compounds from the nucleus, though this activity remains invisible across such vast distances. The comet's orbit tightens further, and its inclination, eccentricity, and orientation in space shift subtly under the combined influence of the Sun, planets, and galactic tides. It is still far beyond any region where planetary interactions occur, but it now falls clearly under the Sun's dominion. From this point, the inward trajectory continues without reversal. The comet has left the deep stillness of the Oort cloud. Ahead lies the middle space of the outer solar system, a realm where sunlight slowly intensifies, where the first hints of coma formation begin, and where motion becomes perceptible across human timescales rather than geological ones. The phantom comet's path now moves into a region defined by faint awakening, where ices respond to heat for the first time in millions of years, setting the stage for the visible transformation that follows. As the comet continues its slow descent from the remote outskirts of the solar system, the Sun begins to grow brighter than any star in the background. At first, the change is almost imperceptible, noticeable only across epochs rather than moments. The nucleus remains cold, dark, and inert. Temperatures rise by fractions of degrees, still far too low to melt or vaporize the dominant water ice locked within the body. Yet the most volatile substances, carbon monoxide, nitrogen, and other low-temperature ices begin to feel the influence of sunlight in ways that matter on a microscopic level. Molecules start to move in nanometer scale shifts, migrating through pores in the nucleus. This process is scientifically accepted. Sublimation of ultravolatiles can begin at enormous distances from the Sun, though it produces no visible activity until much closer. The comet drifts inward along an elongated path shaped by gravitational influences accumulated over preceding millions of years. At hundreds of astronomical units, its orbital speed remains slow, but faster than in the cloud from which it came. Gravity pulls steadily, drawing the nucleus toward a region where solar energy increases enough to drive change. The inward fall remains gentle, the nucleus rotating irregularly its surface, absorbing sunlight so weak that any warmth dissipates almost instantly. This gradual awakening marks the earliest stage of transformation, a shift from complete stillness to the faintest stirrings within the icy matrix. A quiet, poetic detail presents itself in this middle region. The comet's nucleus still occupies a realm where the Sun casts barely a shadow. Light has so little strength that shadows appear more like softened gradients than defined forms. If one could look outward from the nucleus, the planets would remain invisible, and the Milky Way would still dominate the sky. Only the subtle increase in solar brightness felt more than seen distinguishes this position. from the farthest extent of the comet's orbit. A scientific mystery persists concerning how deeply sunlight penetrates the outer layers of a comet at these distances. Some models suggest that sunlight warms only the topmost grains, leaving the interior untouched, while other simulations propose that porous structures allow photons to scatter deep enough to affect subsurface volatiles. No spacecraft has observed a comet at this range, and laboratory studies cannot fully reproduce the conditions. For the phantom comet unseen throughout this phase, these questions remain unanswered. Soft ironies drift across this transition. It takes only faint sunlight to begin altering the most volatile ices, yet the nucleus has travelled billions of kilometres through darkness without change. It takes the gentle heat of a distant star to shift molecules within the nucleus, yet that same heat remains too weak to produce even a visible haze. It takes a drift of millions of years to initiate this activation, yet once it begins, the alteration of the surface accelerates with each step inward. These contrasts shape the quiet rhythm of a body emerging slowly from deep cold. The comet approaches a point where heating becomes measurable, not in the melting of water ice still far too cold for that, but in the release of trapped gases from the pores of its dusty surface. Carbon monoxide and carbon dioxide molecules sublimate, weakly diffusing from the interior to the vacuum surrounding the nucleus. A tenuous envelope of gas forms around the surface, invisible from Earth, and almost undetectable from any vantage except directly beside the nucleus. This early coma remains thin, fragile and transient, with molecules streaming outward, only to disperse within moments. Yet it represents the beginning of a visible transformation that will intensify dramatically as the comet approaches the Sun. A gentle modern analogy helps clarify the scene. This early sublimation resembles the first faint mist rising from frost when a distant dawn begins. The frost remains solid, unchanged in appearance, yet tiny vapours drift from its surface, signalling the arrival of warmth. The comet reacts similarly, silent, faint and undramatic, yet undeniably transitioning. As the nucleus travels inward, the Sun's gravitational pull increases, and its acceleration becomes noticeable over centuries rather than millions of years. Still, the journey remains slow. At dozens of astronomical units, the comet reaches the realm where giant planets orbit, though it remains well outside their paths. Here the Sun's influence strengthens enough to drive continuous activity in the ultra-volatile components. Jets of faint gas, though weak, begin to concentrate near areas of the surface that receive slightly more sunlight due to rotation or irregular topography. The nucleus carries no internal heat. All activity arises from the Sun's increasing energy input. Yet another scientific uncertainty lingers regarding how rotation modulates this early activity. Comet nuclei often spin irregularly, with axes and periods that shift as sublimation exerts small torques on their surfaces. Some nuclei wobble, others tumble. Without observational data, the phantom comet's rotation remains unknown. Whether it spun slowly in a single direction or rotated chaotically, any shift in its spin state across this long inward drift remains hidden from every observer. Several more soft ironies gather around this stage. The comet spends billions of years accumulating volatiles in the dark, yet the earliest release of those volatiles begins while still far beyond any planet. It travels through space unchanged for nearly the entire history of the solar system, yet its transformation begins quietly long before its visible approach to the Sun. It remains entirely invisible to observers, yet the processes reshaping it now will define the appearance it will eventually show in the sky during its fleeting moment of visibility. These observations rest gently within the narrative, reflecting the slow interplay between deep time and brief revelation. The comet moves steadily inward, approaching the colder region of the outer planetary system. At about the orbit of Neptune, sunlight becomes strong enough that sublimation of more robust volatiles increases, feeding a coma that now would appear faintly measurable to a spacecraft if one were present. Dust grains held within the nucleus by weak cohesion begin to detach as escaping gases lift them from the surface. These grains drift away slowly at first, then more quickly as gas production rises. The coma expands into a cloud tens of thousands of kilometers across, though still faint and diffuse. For the phantom comet, unseen and unrecorded through this phase, the process unfolds entirely without witness. No telescope points toward it, no instrument measures its gas production, no observer marks its slow brightening. It remains a solitary body moving along its orbital path, preparing for a future appearance it will make only once in recorded history. As the comet crosses into the region where giant planets orbit, gravitational interactions may shift its path slightly. Jupiter and Saturn, with their substantial masses, influence the motion of long-period comets that pass near their spheres of control. A small change in trajectory can alter the shape of the comet's orbit, adjusting its future perihelion distance or its long-term return time. Whether the phantom comet experienced such an encounter remains unknown. With only a single recorded sighting, reconstructing its earlier journey is impossible, yet the possibility remains consistent with the behavior of other comets whose orbits reveal the influence of planetary gravity. The inward motion now leads toward a region where solar energy increases quickly compared to the distant outer zones. Sublimation will soon transition from a faint release of ultravolatiles to a vigorous outflow of water vapor and dust. The coma will expand dramatically and the tail will begin to take shape. The phantom comet moves toward the point where its long descent will finally make it visible against Earth's sky, its only moment of recorded existence, before continuing its path into the uncertainty that defines the remainder of its orbit. Closer to the Sun within the realm where giant planets have already fallen behind, along the comet's elongated path, the transformation of the nucleus becomes unmistakable. Solar radiation now arrives with enough intensity that water ice near the surface no longer remains inert. Molecules on exposed faces absorb photons, gain sufficient energy to break their bonds with the solid, and escape into the vacuum as gas. This process of sublimation, well established in comet science, turns a previously silent nucleus into an active source of vapor. Gas streams outward in all directions from the surface, carrying with it entrained dust particles that detach from the weakly cohesive matrix. Around the dark core, a cloud forms the coma, a transient atmosphere bound not by gravity for long, but by the continuous supply of escaping material. The coma expands rapidly. Each gas molecule, once freed, moves along a roughly straight path until it collides with other molecules or is broken apart by sunlight. Close to the nucleus, where densities are higher, collisions occur often enough that the inner coma behaves almost like a fluid with gradients of temperature and density forming smooth structures. Farther out interactions become rarer, and the coma transitions into a collisionless regime where individual particles travel along ballistic trajectories. In this extended region, the gas thins until it merges with the surrounding solar wind. Scientific models and spacecraft observations confirm that coma sizes can reach hundreds of thousands to millions of kilometers across, dwarfing the nucleus itself by many orders of magnitude. A quiet poetic detail emerges in this stage. The nucleus remains essentially invisible within its own luminous envelope. A small irregular body of dark ice and dust only a few kilometers across hides inside a sphere of gas and dust far larger than Earth. To a distant observer, only the halo appears gently brightened by sunlight scattered from microscopic particles. The solid origin of the display retreats into shadow, its exact shape and texture erased by the brightness of the coma it sustains. Within this expanding envelope, sunlight initiates a series of photochemical reactions. Ultraviolet photons break water molecules into hydrogen and oxygen dissociate carbon monoxide and carbon dioxide, and ionize some of the resulting fragments. The liberated ions respond to the electric and magnetic fields embedded in the solar wind, beginning to form a structure that will evolve into the ion tail. Neutral fragments continue to travel outward until they either escape the system or are eventually swept away. The composition and distribution of these species reveal the chemistry of the nucleus, yet a scientific mystery lingers around the fine-scale arrangement of active regions. Observations show jets, fans, and asymmetries, but the detailed pattern of fractures, pores, and compositional layers beneath the surface that produce these features remains only partly understood. Soft ironies drift through this scene. It takes only a relatively thin veneer of sunlight to drive a coma that extends across distances larger than many planetary diameters, yet that same sunlight previously left the nucleus untouched for billions of years in deep space. It takes only a fragile mixture of dust and ice to create a structure visible across tens of millions of kilometers, yet the nucleus itself remains so dark that it reflects only a small fraction of the light that reaches it. It takes only a brief perihelion passage to release gas and dust that have been stored since the solar system's earliest epochs, yet those materials disperse into space in a matter of weeks or months. As the comet approaches the orbits of the inner planets, its coma thickens near the nucleus. Gas production increases steeply, with decreasing distance from the Sun following well-studied temperature dependencies. The surface does not warm uniformly. Instead, some regions oriented more favourably toward the Sun become more active, driving jets that punch through the surrounding gas. These jets follow the local topography and fractures responding to subsurface reservoirs of volatile rich material. When the nucleus rotates, these jets sweep through space like slow fountains, imprinting spiral structures into the inner coma. Observations from spacecraft around other comets confirm that such features arise from the complex interplay of shape spin and solar illumination. A gentle modern analogy can frame this behaviour. The nucleus resembles a dark, slowly turning stone under a bright lamp, with patches that release faint steam where the light falls more directly. The lamp in this case is the Sun, the stone a mixture of ice and dust, the steam the escaping gases that build the coma. Yet unlike the familiar analogy, the scale here is astronomical, and the faint vapour grows into a vast, nearly spherical envelope. Within the coma, dust grains of various sizes follow different paths. Fine particles remain coupled to the gas flow streaming outward in approximate radial directions from the nucleus. Larger grains, less affected by gas drag, follow orbits that deviate from strict radial lines influenced more by the nucleus's gravity and their initial ejection velocities. The distribution of grain sizes shapes how the coma scatters sunlight, setting its brightness profile and apparent colour. Some comets show comae with subtle hues, slightly bluer or redder than the solar spectrum, depending on dust composition and particle size distribution. For the phantom comet, such details go unrecorded. Its single appearance leaves no spectral measurements, only general descriptions of brightness and shape. Another scientific uncertainty rests in how internal structure determines the timing and intensity of activity. Some comets begin to display coma and tail features at relatively large distances. Others remain faint until they approach much closer to the Sun. Differences in composition, porosity, and previous thermal history all contribute, but the exact weighting of these factors for any single nucleus remains difficult to quantify. Without repeated observations or in situ measurements, the phantom comet's specific behaviour can only be placed within the broad patterns established by other long-period comets. Soft ironies continue to accompany the comet's transformation. It takes only the thin outer shell of the nucleus to generate most of the observable activity, yet the bulk of the body remains unchanged inside, preserving a record of conditions that no light can reach. It takes only a narrow range of distances from the Sun to trigger full coma formation, yet the comet's orbit spans a vast radius from the inner system back to the outer cloud. It takes only a small delay in observation-clouded skies, missing instruments for an entire cycle of coma growth and decay, to pass without detailed record even though the underlying physics is well described. As the coma expands and brightens, the comet becomes visible to ground-based observers, equipped with telescopes and sometimes even to unaided eyes under dark skies. The phantom comet, when it finally crosses this threshold, appears as one more diffuse patch among many recorded in astronomical catalogues, a modest central condensation surrounded by a hazy envelope, perhaps with the first hint of a tail extending away from the Sun. The physical processes that produce this appearance are the same for all such bodies: sublimation, gas expansion, dust entrainment, and photochemistry. Yet each comet's coma carries a unique signature of composition, activity pattern, and viewing geometry. In the narrative's slow movement inward, the coma marks the comet's first visible breath of light. A once inert nucleus now surrounds itself with a luminous shell, not through any internal fire but through sunlight acting on ancient ices. Ahead lies the region where this envelope will stretch into distinct tails, under the combined influence of radiation and the solar wind turning a spherical haze into the elongated forms that observers most often associate with comets. The phantom comet advances toward that zone, its brightening coma both a cloak around its nucleus and a prelude to the tails that will soon extend behind it. As the comet moves still closer to the sun, the coma that once appeared nearly spherical begins to stretch and thin in the direction away from the star. Sunlight, which previously only warmed the surface enough to drive gas outward, now exerts mechanical influence on the dust grains embedded within that gas. Each particle, tiny and irregular, intercepts photons that transfer momentum to it, pushing it gently but persistently away from the sun. This process radiation pressure is a scientifically accepted explanation for the formation of a dust tail. While gravity pulls both the nucleus and its surrounding particles toward the sun, radiation pressure counteracts that pull for the smallest grains, bending their trajectories outward. Over time, these altered paths accumulate into a broad curved tail, composed of myriad dust particles, all slowly drifting away from the nucleus, along similar though not identical arcs. Within this dust tail, particles of different sizes follow subtly different journeys. Larger grains, more massive compared with the momentum they receive from photons, deviate only slightly from the comet's orbit. They trail behind in a path that closely follows the nucleus. Smaller grains, more susceptible to radiation pressure, are pushed outward, more effectively forming a tail that sweeps gently away from the direction of motion. The result is a tail that curves, tracing a broad, soft arc that can stretch for millions of kilometers. Observations of many comets confirm this behavior. Dust tails tend to appear wide, diffuse, and slightly yellow or white when illuminated by sunlight scattered off their surfaces. The phantom comet's dust tail, if seen clearly, would have shared these properties, although details of its brightness and length remain unrecorded. A poetic detail appears in this extended structure. Each grain in the dust tail reflects sunlight, the way fine dust motes reflect light in a darkened room, visible only because illumination catches them at a certain angle. The tail itself is not solid. It is a vast collection of tiny separate particles, each following its own orbit, yet from a distance they merge into a single continuous streak. In this way, the tail resembles a faint brushstroke across the sky, drawn not by a single sweep, but by countless individual paths layered over one another. While the dust tail curves gently under radiation pressure, a second structure forms under a different influence. As gas in the coma is ionized by ultraviolet sunlight, the resulting ions feel the effects of the magnetic field carried by the solar wind. Rather than moving primarily under gravity and radiation pressure, these charged particles are guided and accelerated by electromagnetic forces. They are swept away from the comet along field lines and flow into the solar wind, forming what is known as the ion tail. This tail tends to be narrower, straighter, and often bluish when observed, pointing more nearly directly away from the sun, regardless of the comet's direction of travel. Instruments and images from many comet encounters confirm that ion tails can contain fine filamentary structures, knots and kinks produced by interactions with variable solar wind conditions. A scientific mystery remains within these ion tails. Although models describe how the solar wind and interplanetary magnetic field interact with cometary ions to produce the observed forms, the detailed evolution of fine features, sudden breaks in the tail disconnection events where entire segments appear to be severed, and rapid changes in brightness depend sensitively on the local plasma environment. Variations in the solar wind, such as shocks or changes in magnetic orientation, can cause abrupt rearrangements in the tail, but predicting the exact timing and shape of these changes remains challenging. For the phantom comet, no such detailed observations exist, leaving its ion tail structure entirely within the realm of unmeasured behavior. Soft ironies drift through this dual tail configuration. It takes only a small dark nucleus a few kilometers across to generate tails that can extend tens of millions of kilometers into space. It takes only thin sunlight and a tenuous wind of charged particles to sculpt these enormous structures, yet those same forces are too gentle to disturb the planets they pass. It takes only a short passage near the Sun for these tails to appear at full splendour, yet they disperse quickly after perihelion, leaving no enduring trace in the inner solar system. These contrasts rest quietly in the physics of light gravity and magnetism. A modern analogy presents itself softly. The dust tail resembles a slowly drifting plume of smoke spreading and curving under a steady breeze, while the ion tail resembles a faint beam shaped by an invisible flow of charged air. Both are intangible, both shaped by forces that cannot be seen directly, and both exist only while the source remains active. Once gas production falls or the comet retreats from the Sun, these tails thin and vanish, returning their material to the general population of dust and plasma that permeates the heliosphere. Within the dust tail, individual grains follow orbits that will in many cases persist long after the comet itself has moved on. Some remain near the comet's path, forming a trail of particles that can at later times intersect planetary orbits. When a planet such as Earth passes through such a trail, tiny grains enter the atmosphere and burn up due to friction, with the air producing brief streaks of light known as meteors. When many such grains arrive in a short interval, a meteor shower occurs. In this way, a tail that seems to vanish after the comet's passage leaves behind a subtle, enduring effect in the form of dust streams. Whether the phantom comet generated any such stream remains unknown, but the possibility fits within the established behaviour of many comets whose debris has been tied to known meteor showers. In contrast, ions in the ion tail rarely persist as coherent structures for long. They are quickly carried away and mixed into the solar wind, losing their connection to the comet that released them. Their role is more transient, yet equally revealing the shape and motion of the ion tail record, the local conditions of the solar wind acting as a kind of tracer for the invisible flow of plasma around the comet. Spacecraft that have flown through such tails have detected changes in magnetic field plasma density and particle composition, confirming the picture that ion tails function as channels through which the solar wind and cometary material exchange energy and particles. Additional soft ionies accompany these processes. It takes only the brief interval of a comet's near-Sun passage to seed the inner solar system with dust that may linger for thousands of years, yet the tails that first reveal this dust appear only for weeks or months. It takes only minor differences in grain size and charge to produce distinct dust and ion tails, yet from a great distance both may blur into a single diffuse feature to the unaided eye. It takes only modest changes in solar wind conditions to reshape the ion tail dramatically, yet the comet's nucleus continues along its orbit largely unaffected by those same changes. As the phantom comet traverses this region, its dust and ion tails form, evolve and extend behind it. To observers on Earth under sufficiently dark skies and with favourable geometry, the dust tail might appear as a soft, sweeping fan, while the ion tail could form a thinner, straighter ray pointing away from the Sun. Together they mark the comet's path not by tracing where it has been exactly, but by showing the flow of material released along its journey. The nucleus moves onward along its orbital path while the tails continually rebuild and disperse, never quite the same from one moment to the next. In the narrative's slow movement, this stage represents the comet's most recognizable form, a luminous head and trailing tails shaped by events at the surface and by fields and radiation in the surrounding space. Ahead lies the region where human observers measure positions and brightness, attempting to reconstruct orbits from short observational arcs, and where the phantom comet's single recorded appearance enters the catalogues that preserve its brief presence in Earth's sky. As the comet moves through the inner solar system with a bright coma and distinct tails, its physical processes continue indifferent to whether any eye or instrument notices. Yet against the dark of night on one small planet, telescopes and patient watchers turn toward the sky, recording its brief passage as positions marked against known stars. For astronomers, a comet is measured not by the texture of its nucleus, or the chemistry of its coma, but first by where it appears and how that position changes with time. The sky is treated as a vast coordinate grid, and each sighting becomes a point on that grid written down with date, time, and reference stars. This method is an accepted foundation of celestial mechanics. From a series of angular positions, the path of a body under gravity can be inferred, at least in principle, even when the body itself remains a distant blur of light. In the era before digital detectors and automated surveys, each observation requires careful alignment of telescope steady tracking and the patient comparison of a moving point with the fixed lattice of background stars. Charts and catalogues list those stars with known positions, and a comet's location is expressed relative to them. Repeated measurements over nights and weeks create a trail of coordinates. The rate at which the object changes position on the sky and the direction in which it moves provide the first hints of its orbit. Near-Earth comets shift noticeably from night to night. Distant ones move more slowly. In both cases, the essential data are the same: right ascension and declination at specific times, each point capturing a moment in the comet's passage. A quiet, poetic detail lives in this process. On each observing night, the comet shares the sky with constellations that barely change over human lifetimes. While stars maintain their patterns shifting only over millennia, the comet slides gently among them, leaving a short-lived trace in notebooks and photographic plates. The fixed stars act as a stable backdrop against which transient objects can be measured, so that a body that will not return for tens of thousands of years is pinned for a brief interval to a grid defined by lights that outlast it. From these positions, astronomers construct a preliminary orbit. A scientifically accepted method developed over centuries allows an orbit under Newtonian gravity to be estimated from as few as 3 well-timed observations, though more improve reliability. The orbit may be approximated as parabolic if only the near-Sun passage is sampled or refined to an ellipse or hyperbola when longer arcs are available. For many comets, especially those returning frequently, dozens or hundreds of measurements permit a detailed solution. For others, only a small number of points exists, and the resulting orbit acquires large uncertainties. The Phantom Comet belongs to this latter class, brief arc sparse data, and a solution that can be drawn but not trusted with confidence. A scientific mystery remains rooted in such cases. When the observational arc is short and the comet's motion is measured for only a few days or weeks, the derived orbit can fit many possible futures. Slight changes in assumed positions or in the weighting of each measurement can shift the estimated eccentricity from bound to unbound. The object may be classified as long-period, potentially returning after immense intervals, or as a one-time visitor on a hyperbolic trajectory never to be seen again. Without additional data, no unique answer appears. The Phantom Comet's status as a lost object reflects precisely this ambiguity. The mathematics allows several plausible paths, and no observation resolves which one nature chooses. Soft ironies drift through this scene of careful measurement. It only takes a few recorded positions to demonstrate that the comet moves under the same gravitational laws that guide planets, yet it may take far more observations than exist to predict its future path reliably. It only takes a modest telescope and clear skies to notice the comet's motion among the stars, yet it takes an entire framework of celestial reference systems and timekeeping to turn those motions into orbital elements. It only takes a single cloudy week during the comet's fastest changes to prevent the collection of critical points leaving the orbit forever uncertain. These small contingencies sit quietly beside the precise laws that otherwise make celestial motion predictable. Early photographic plates add another layer. When plates capture wide fields of the sky, a faint streak of light crossing among star images can later be measured with microscopes and measuring engines. The positions of stellar images define the plate's mapping to celestial coordinates, and the comet's streak yields a position at the time of exposure. Even decades later, archival plates can be re-examined with improved techniques, refining old measurements, or revealing unnoticed comets near the detection threshold. Yet for some apparitions, such retrospective searches find nothing more than the few already known records. In those cases, as with the phantom comet, the observational footprint remains stubbornly small. A gentle analogy arises: the set of comet positions resembles footprints left briefly in fresh snow. Each print marks a definite place at a definite time, but if the trail is incomplete, the path may be inferred inaccurately or not at all. Wind-new snowfall or simple gaps in where the path crosses the observer's field can erase critical steps, leaving only a partial record. In the sky, clouds, daylight, and the geometry of Earth's orbit play similar roles, removing opportunities to see the comet and leaving observers with only a fragment of its journey. Another soft irony sits in the relationship between sky coverage and discovery. It takes only a narrow strip of sky scanned at the right time to detect a comet and record a few positions, yet it takes systematic coverage of large portions of the sky over many nights to follow that comet long enough to secure an orbit. It takes only modest equipment to notice that a new fuzzy object has appeared, yet it takes coordinated networks and modern surveys to ensure that such objects are tracked consistently from first detection to fading. In earlier times, the imbalance between discovery and follow-up meant that some comets once announced slipped away before their paths could be fixed. For orbit determinations, uncertainties often concentrate in specific parameters. When a comet is observed near perihelion, its sky motion can reveal the orientation of its path and an approximate shape, but its period remains poorly constrained. Extrapolating backward and forward along the estimated orbit extends the predicted positions into times when it is too faint to be seen. If the true orbit differs slightly, even by small amounts, the predicted path diverges over years and decades. Attempts to recover the object at later returns then point telescopes to empty regions of sky. The comet has not become invisible through any unusual physics. The predicted coordinates have simply slipped away from reality. The phantom comet's absence on subsequent searches exemplifies this quiet divergence between calculation and nature. Another scientific uncertainty lies in non-gravitational effects. As comets outgas, jets of escaping gas can exert small but cumulative forces on the nucleus, slightly altering its trajectory from that predicted by pure two-body gravity. These effects depend on the distribution of active regions on the surface, the rotation state, and the rate of gas production. In many well-observed comets, including some that revisit the inner solar system frequently, such non-gravitational terms can be measured and included in orbital models. For a comet with only a few positional measurements, such corrections cannot be estimated. They remain hidden within the already large uncertainties of the orbit. Thus, even if the phantom comet's future path is altered by outgassing, no information exists to quantify that change. Soft ironies continue to accumulate. It only takes a slight asymmetric outflow of gas to shift a comet's path by thousands of kilometers over one orbit, yet that shift may remain invisible in the sparse data. It only takes a few seconds of additional exposure time on a cloudy night to have captured a crucial position, yet that exposure is never taken. It only takes the same physical processes that make the comet visible outgassing and jetting to complicate the task of predicting where it will be visible again. The source of information becomes simultaneously a source of uncertainty. Through all of this, the comet itself continues its motion without concern for coordinates or catalogues. The phantom comet passes, perihelion brightens, displays its tails, and then recedes. Astronomers mark its positions while they can calculate an orbit as well as the data allow, and record both observations and uncertainties in ephemerides. When the comet fades beyond the reach of telescopes, the record remains fixed in journals and catalogues. Over time, the entry is revised, annotated, perhaps flagged as a lost object. The physical body, meanwhile, travels onward along whatever path nature has set, either bound to return after a very long interval or slipping permanently into interstellar space. In the slow ambient narrative of celestial mechanics, this stage marks the intersection between physical processes in the comet and intellectual processes on Earth. The tails and coma respond to sunlight and the solar wind. The nucleus follows gravity and subtle outgassing forces. At the same time, observers trace its brief apparition against the stars, building an incomplete but scientifically grounded description of its path. Ahead lies the region of the story where that incompleteness becomes decisive, where a short observational arc, a set of real but limited data, leaves the comet's ultimate fate uncertain, and the phantom remains a visitor seen once, and then not again. After the comet's brief passage across the inner sky, the record that remains consists of a small set of positions, brightness estimates, and perhaps a few descriptive notes about the shape of its coma or the length of its tail. These entries, while precise in the context of individual observing nights, form only a thin slice of the comet's full trajectory. Celestial mechanics, using Newton's laws and the mathematics of orbital determination, can take such points and produce an orbit that fits them. When the arc of observation is long and the data are numerous, this fit becomes tight. When the arc is short and the data sparse, a whole family of orbits can satisfy the same measurements. This is a scientifically accepted difficulty with limited observations. A comet's path becomes under-constrained, and predictions of its future position grow uncertain. The phantom comet occupies this uncertain regime. In practice, the process begins with the observed right ascension and declination of the comet, at several times corrected for Earth's rotation, atmospheric refraction, and the motion of the observing sight. These coordinates define lines of sight into space. The task is to find a path, a conic section under the sun's gravity, that passes through all these lines of sight at the recorded times. For many comets, initial orbit solutions assume a parabolic trajectory, a reasonable approximation when only the near perihelion passage is sampled. Later, as more data accumulate, the orbit can be refined to an ellipse for bound comets, or a hyperbola for unbound ones with a specific eccentricity and period. For the phantom comet, the limited arc leaves the eccentricity poorly determined. Small changes in the input positions or assumed outgassing effects can tilt the solution one way or another without violating the observations. A quiet poetic detail lies in the way these uncertain paths are described. They appear as lines of numbers in ephemerides, predicted positions for future dates, each one carrying implicit assumptions about the orbit's shape. The comet's future is written as a sequence of coordinates that stretch into years and decades. On paper, the track looks fixed. In reality, each entry holds a hidden spread, a region of sky where the comet might appear rather than a single point. For the phantom comet, these predicted positions drift away from reality as time passes. Telescopes later pointed along the ephemeris line find only empty fields studded with the same enduring stars. A scientific mystery persists in such cases. The true orbit, the one path that the comet actually follows, remains unknown even though its existence is certain. The mathematics guarantees that there is one solution defined by the comet's initial conditions and the forces acting upon it, but with only a brief observational window, no method can uniquely recover it. Additional uncertainties arise from non-gravitational forces due to outgassing from measurement errors and from possible small perturbations by planets. Each of these effects can alter the orbit subtly, but when observations are sparse, they cannot be disentangled. The phantom comet's actual trajectory continues precise and singular, while human knowledge of it remains a closed interval bounded by the dates of observation. Soft ironies unfold quietly around this fading track. It takes only a single gravitational law to describe the comet's entire motion, yet it takes many more observations than exist to reconstruct that motion with confidence. It takes only a few nights of clear skies to anchor an orbit tightly, yet a week of poor weather or an inconvenient geometry can remove those nights from the record forever. It takes only a straightforward application of known physics to project the comet's path far into the future, yet the missing information ensures that those projections will likely place it in the wrong patch of sky. Another soft irony appears in the contrast between past and future precision. Positions observed during the comet's apparition are known with high accuracy. They can be remeasured from preserved plates or logs, yielding coordinates to arc-second scales. Yet the farther those positions are extrapolated forward or backward in time, the wider the envelope of uncertainty becomes. The past and present are sharply defined. The future spreads out into a diffuse possibility. In the case of the phantom comet, this diffusion becomes so wide that the object is effectively lost, even though its motion remains in principle entirely deterministic. A third quiet irony lies in the dual role of activity. The same gas jets that make the comet visible driving coma and tail also exert small reactive forces on the nucleus. These forces alter the orbit slightly, shifting the path away from that predicted by gravity alone. For comets observed many times, these non-gravitational terms can be fitted from the data and included in updated orbital elements. For a comet like the phantom one seen only briefly, these subtle accelerations cannot be quantified. The outgassing that reveals the comet's presence simultaneously adds uncertainty to its future course, a reminder that visibility and predictability do not always align. A gentle analogy offers another perspective. The comet's observed positions resemble a short fragment of a long-written sentence copied into a notebook, while the rest of the sentence remains unread. From that fragment, the structure of the language can suggest how the sentence might continue, but multiple continuations are consistent with the same opening. Without the rest of the text, no one can know which continuation is correct. The orbit solutions derived from limited observations are like those plausible continuations, mathematically consistent yet incomplete, each one an approximation of a path that only nature knows in full. In the decades following the phantom comet's sighting, astronomers may return to the recorded observations, applying improved methods and updated models. They might search archival images taken around the time of the original apparition, hoping to find additional exposures that extend the arc. They might update gravitational constants, planetary ephemerides, and even include estimates of non-gravitational terms. Each revision narrows or shifts the family of possible orbits. Yet without new sightings, the process eventually reaches a limit. The predicted time of return, if the comet is bound, might span decades or centuries. The predicted sky location might cover swaths too large to search effectively. At that point, catalogues may mark the object as lost, acknowledging that the recorded arc is too short to support reliable recovery forecasts. Another scientific uncertainty settles around the question of the comet's physical survival. Some comets disintegrate during their passage near the Sun, fragmenting into smaller pieces that drift apart and fade. Others lose only a surface layer and remain largely intact. Without detailed monitoring, it's impossible to know which outcome occurred. The phantom comet could follow either path. It may continue on a very long period orbit, its nucleus weakened, but surviving, destined to return after tens of thousands of years to an entirely different configuration of planetary orbits and observers. Or it may have released enough material during its apparition to destabilize its structure, breaking apart into fragments too small and faint to be recognized as a returning body. Both scenarios fit comfortably within what is known about comet behavior. Soft ironies gather once more around this ambiguity. It takes only a single perihelion passage to weaken a fragile nucleus significantly, yet the outward appearance of the coma may not betray the extent of internal damage. It takes only a small fragment to carry on the original orbit, yet if that fragment is too small, it no longer registers as a comet from Earth's vantage point. It takes only one disintegration event to end the comet's individuality as an object. Yet the dust and gas released continue to travel under the same gravitational rules, becoming part of broader meteoroid streams or interplanetary dust populations. The comet's identity as recorded in catalogues may fade while its material persists in more diffuse forms. For the phantom comet, the record now lies mostly on paper and in digital archives. Observations are preserved not in the sky, where the object once glowed, but in tables of numbers and short descriptions. The track as far as measurement allows is known. Beyond that, it fades into uncertainty. The physical body remains somewhere along whatever path its initial conditions and subsequent perturbations dictate, moving through space with no need of being found. The contrast between the comet's ongoing existence and the fading of its orbit from human knowledge forms a quiet boundary in the narrative, a point where physics continues cleanly, while observation and prediction grow dim. From this stage, the story turns naturally toward trajectories that by their nature do not repeat in any practical sense. Some comets arrive on paths so extended or so open that for all intents and timescales relevant to planetary history, they are one-time visitors. The phantom comet may belong to this class, or it may simply follow a period so long that its next return lies beyond the span considered. In both cases, it becomes for astronomers and records alike a presence that appeared once left its numerical trace, and then receded into a pattern of motion that continues whether or not it is ever seen again. In the family of possible orbits under the Sun's gravity, some paths close, gently back on themselves, while others open outward and never return. Ellipses describe bound motion, the kind traced by planets and most short-period comets, while parabolas and hyperbolas mark trajectories that either barely remain bound or escape entirely. This classification follows from the total orbital energy of the body. If that energy with respect to the Sun is negative, the orbit is closed. If it reaches zero or becomes positive, the path opens. In practical comet science, many long-period comets appear near perihelion on orbits so stretched that they are nearly parabolic with eccentricities close to 1. Some of these are truly bound, destined to return after hundreds of thousands or millions of years. Others with only slightly higher energies follow hyperbolic paths that lead them out of the solar system forever. The difference between these cases can be small in speed, but its consequences extend across all future time. When a comet arrives on a near-parabolic orbit, its speed near perihelion almost matches the local escape speed from the Sun. At Earth's distance, the escape speed from the Sun's gravity is on the order of tens of kilometers per second, and a long-period comet passing at that radius can move at comparable velocities. Even small additional accelerations from planetary encounters or asymmetric outgassing can tilt such an orbit from marginally bound to unbound. A close pass by Jupiter or Saturn can exchange energy between the comet and the planet, slightly increasing or decreasing the comet's heliocentric speed. In one direction, the orbit shrinks and the period shortens. In the other, the eccentricity grows beyond unity, and the body is set on a hyperbolic trajectory. The phantom comet seen once and then not again fits comfortably into this dynamical framework, even if its actual eccentricity remains unmeasured. A quiet poetic detail resides at perihelion. On a nearly open orbit during that brief interval near the Sun, the comet's velocity and direction are such that a change too small to notice visually decides whether it will ever return. The nucleus rushes through its closest approach in a matter of days or weeks, outgassing, shedding dust, and interacting gravitationally with nearby planets. Within that narrow window, the sum of all forces determines whether the orbit bends into a closed curve or opens into a path that only passes once. From the comet's own perspective, if such a perspective could exist, there is no threshold, only smooth motion. The distinction between bound and unbound appears only when the orbit is extended conceptually into the far future. A scientific mystery persists in the statistics of these nearly open trajectories. Catalogues of long-period comets show that many arrive on orbits that appear slightly hyperbolic when fitted to limited observational arcs. In some cases, this hyperbolicity may be real, indicating visitors that fall through the solar system once before returning to the galactic background. In others, the apparent excess energy likely reflects measurement uncertainties or unmodelled non-gravitational forces. Distinguishing between these possibilities requires long arcs of precise observation, which are rarely available for faint transient comets. The phantom comet's recorded path could fall on either side of this subtle divide. Without additional data, it remains unclear whether it belongs to the population of distant Oort cloud objects sent inward by galactic tides, or to a rarer class of bodies on genuinely escaping orbits. Soft ironies accompany this uncertainty. It takes only a fraction of a kilometre per second of extra speed to convert a bound orbit into an escaping one, yet that difference may remain hidden within the noise of positional measurements. It takes only a single close encounter with a giant planet to alter a comet's fate for the entire future of the solar system. Yet that encounter may last only hours and leave no direct record. It takes only a brief interval near perihelion to decide whether the comet will ever return to the inner system, yet the consequences of that interval unfold across millions or billions of years. These ironies rest quietly in the contrast between short-lived interactions and long-lived outcomes. Another set of soft ironies appears when considering perspective. From the standpoint of the Sun, a hyperbolic comet is a visitor that arrives, swings around once, and then drifts outward until its path blends with that of the background stars. From the standpoint of the comet's origin region, whether that region is the Oort cloud or interstellar space, the passage through the inner solar system is a minor perturbation in a journey that spans vast distances. From the standpoint of observers on Earth, the same passage may be the only opportunity ever to record the object. The same trajectory described by a single mathematical curve carries different meanings depending on where and when it is considered, yet the orbit itself remains indifferent to all such viewpoints. A gentle analogy frames these paths that do not repeat. A comet on a hyperbolic or nearly hyperbolic orbit resembles a stone thrown from a valley over a distant ridge. If the stone's speed falls just short of what is needed, it arcs upward, slows, and eventually returns to the valley along a mirrored path. If the speed crosses the threshold by a small margin, the stone crests the ridge and continues onward into another landscape never to come back. The ridge corresponds to the escape energy from the Sun, and the comet's velocity near perihelion determines on which side of that ridge its future lies. The physical processes that impart or remove the final increment of speed, the tug of a planet, the recoil from outgassing jets act like subtle changes in the throw. Within the population of long-period comets, many are on orbits that are effectively non-repeating on human timescales, even if technically bound. A comet with a period of several million years will not return while any present system of record-keeping remains, nor while continental positions on Earth stay as they are. For practical purposes, such an object behaves like a one-time visitor. The phantom comet may occupy this category, bound in principle, unreturning in practice. In catalogues, its orbital elements may list a formal period, yet that number holds little operational meaning. No one now alive and no direct descendants of current instruments will be present when such a cycle completes. Soft ironies emerge here as well. It takes only a small shift in orbital parameters to change a comet's nominal period from hundreds of thousands of years to millions, yet both options place its return far beyond any conceivable observing program. It takes only one entry in a catalogue to mark that an object has been seen, yet the interval until its next appearance may be so long that the original catalogue, the language in which it is written, and even the present arrangement of oceans and continents will have changed. It takes only a simple classification, long period, nearly parabolic, possibly hyperbolic, to summarize the comet's status, yet that classification folds together a wide range of actual dynamical histories. One final soft irony lies in the way such paths are recorded. It takes only a few nights of favourable geometry and clear weather for a comet's orbit to be fitted and assigned a designation that encodes its dynamical type. It takes only a short note to indicate that the orbit is uncertain, nearly parabolic, or possibly hyperbolic. Yet behind those few words stand processes that span from the early shaping of the Oort cloud to the present state of the galactic neighbourhood. In the ambient narrative of its passage, the phantom comet moves through perihelion on a path that likely does not repeat in any meaningful human sense. Whether technically bound with a period too long to matter, or truly unbound on a hyperbolic orbit, it leaves the inner system after a single recorded visit, its tail's fading coma, thinning nucleus, cooling back toward the temperatures of the outer dark, and its future motion, merging gradually into the larger pattern of distant icy bodies and interstellar wanderers. As the comet approaches and passes perihelion, the balance between what holds its nucleus together and what pulls it apart reaches its most delicate point. The The same sunlight that awakened the ices in the outer regions now heats the surface strongly enough that sublimation proceeds at intense rates. Large amounts of gas escape from the top layers, carrying dust and small fragments with them. Jets open and close as rotation exposes different regions to the sun. Thermal gradients build between sunlit and shadowed faces, producing stresses within the porous structure. The nucleus, once a quiet repository of ancient ices, becomes a place where fractures grow voids, expand, and material near the surface is removed layer by layer. This behavior is scientifically confirmed by observations of some comets that fragment or fade dramatically near their closest approach to the sun. In some nuclei, cohesive forces and internal structure are sufficient to withstand these stresses. The body loses material but remains largely intact, rounding its edges and exposing fresh layers for future passages. In others, the structure proves more fragile. Differences in composition, porosity, and pre-existing fractures combine so that sections of the nucleus break away. A single body becomes several, each smaller than the original. These fragments may continue along nearly the same orbit, briefly forming a small train of comets that share a common path. Some of them disintegrate further, breaking into clouds of dust and gravel. Over time, their collective brightness may drop below detectability, leaving only a diffuse trail of debris along the orbital path. A quiet, poetic detail lies in the way such disintegrations can appear. Instead of a single sharp nucleus at the centre of the coma, a faint elongation, or a set of small condensations may emerge, each one a piece of the former whole. The coma becomes asymmetric, stretching along the direction of motion, and the tail acquires subtle structures as dust released from each fragment mixes into the flow. To a distant observer, the comet seems to soften its definite core, replaced by a more diffuse transient glow. Eventually, even these features fade until nothing distinguishes the comet from the general background of interplanetary dust. A scientific mystery persists regarding which comets will survive perihelion and which will not. While some correlations exist, such as between small perihelion distance high activity and increased likelihood of breakup, no definitive predictive rule has emerged. Two comets of similar size and composition can behave differently, one remaining intact, the other fragmenting. Internal structure, such as layering void distributions and the presence of weak zones, likely plays an important role, but these properties cannot be measured directly for most nuclei. In the case of the Phantom Comet, no detailed monitoring accompanied its passage, so whether it shed only surface layers or broke into fragments remains unknown. Its disappearance from observation could signify either gradual fading as it recedes, or physical disintegration near or shortly after perihelion. Soft ironies rest gently within this uncertainty. It takes only one close passage to the Sun to erase a nucleus that has persisted since the early solar system, yet the external appearance of the coma may show only a smooth brightening and fading to distant observers. It takes billions of years to assemble and preserve the fragile structure of a comet in the outer dark, yet only a few weeks of intense heating at perihelion to dismantle it. It takes careful long-term observation to distinguish between a comet that has simply grown too faint to see and one that has physically ceased to exist as a coherent body, yet many apparitions, including that of the Phantom Comet, pass without such continuous monitoring. As disintegration proceeds, the mass that once resided in a single nucleus spreads along the orbit. Dust grains and small fragments follow paths controlled by gravity and radiation pressure, forming a growing stream of material. Over time, this stream can evolve into a meteoroid trail that intersects planetary orbits. When Earth's path crosses such a trail, the atmosphere experiences an increased rate of small impacts visible as meteors. Some known meteor showers have been linked to past comet disintegrations where the parent nucleus no longer exists as a distinct object. In such cases, the comet has effectively ended, yet its debris continues to create observable phenomena long after the nucleus has vanished. Whether the Phantom Comet has left such a legacy remains unconfirmed. The meteoroid stream it might have produced could be too sparse, too widely dispersed, or too weakly correlated with its original orbit to be identified. Another soft irony appears here. It takes only a brief burst of cometary activity near perihelion to release material that will intersect Earth's orbit for centuries or longer, yet the parent comet may no longer be present for those later encounters. It takes only small grains of dust to create vivid streaks in the atmosphere, yet those grains originated in a body that was itself barely visible. It takes only a narrow band of orbital space to host a meteoroid stream, yet the planets and their observations must align with that band at the right time to notice it. The phantom comet could, in principle, have contributed to such a stream while remaining unrecognized as its source. In some cases, comet breakup is not gradual but sudden. Stresses accumulate until a threshold is reached, and the nucleus fractures catastrophically. Observations of certain comets show abrupt decreases in brightness, followed by the appearance of multiple fragments, or the total disappearance of a central condensation. These events can occur near perihelion, where heating is strongest, or at larger distances where rotational spin-up induced by asymmetric outgassing can exceed the structural strength of the nucleus. The debris spreads along the orbit, sometimes leaving only a dust cloud that quickly becomes indistinguishable from the general background. Without continuous observation, such an event can go largely unnoticed, particularly if the original comet was faint. For the phantom comet, a similar fate remains a plausible but unverified outcome. A gentle analogy helps crystallize this stage of the story. The disintegrating nucleus resembles a piece of porous chalk exposed to a running stream. At first, only the outermost surfaces erode, releasing fine particles into the flow. Over time, water penetrates fractures, widening them, until the piece breaks into smaller parts that dissolve more quickly. Eventually, nothing remains but dispersed sediment carried downstream. In the comet's case, sunlight and sublimation replace water, and the downstream path is the orbit around the Sun, but the progression from intact to fragmented to diffuse remains comparable. Yet another set of soft ironies settles over the end of a fragile nucleus. It takes only thin sunlight distributed over the surface to drive the gas jets that both reveal and undermine the comet's structure, yet that same sunlight remains far too weak to alter the orbits of massive planets. It takes only small internal voids and fractures to determine whether a nucleus can endure repeated passages, or fails on its first close approach, yet those internal details may never be observed directly. It takes only the same processes that produce the beauty of Comet and tail sublimation gas flow dust release to also erase the solid body that initiated them, turning what began as a discrete object into a widely dispersed cloud. For the phantom comet, the narrative accepts that its later condition is unknown. After its single recorded apparition, it could remain on a long-bound orbit, its nucleus weakened but intact, cooling again in the outer dark, destined to return after an interval too long to matter for human records. Alternatively, it could have broken apart near or after perihelion, its pieces dissolving into dust that now drifts invisibly along its former path. In either case, the result within the inner system is similar. No identifiable nucleus returns to the same region of sky, under the same designation, and attempts at recovery find nothing. The comet becomes a phantom not by ceasing to obey physical laws, but by following them into regimes where its individual presence merges with the more general population of scattered debris. In this stage of the story, an object that once formed quietly in the outer solar system travelled inward over immense timescales and briefly brightened near the Sun can end without leaving a clearly recognisable remnant. Its material persists redistributed into dust streams and interplanetary particles, while its identity as a named comet fades from view. Ahead, the narrative moves outward again, following the path of the sparse grains and fragments that continue along the orbit where a singular nucleus once travelled, and considering how these remnants persist in the solar system, long after the parent body has passed beyond the reach of direct observation, long after the comet's active nucleus has passed perihelion, and either receded into the outer darkness, or broken apart near the Sun, the material it released continues its own quiet motion. Dust grains and small fragments freed from the nucleus by outgassing and thermal erosion continue to orbit the Sun according to the same gravitational rules that once guided the parent body. Each grain follows a path that is initially similar to the comet's orbit, sharing its inclination, eccentricity, and general orientation. Over time, however, additional processes, radiation pressure, Poynting-Robertson drag, and gravitational perturbations from planets subtly modify these trajectories. The result is a meteoroid stream, a diffuse elongated collection of particles spread along the original path circling the Sun long after the source has vanished from view. This behavior is scientifically well established, linking certain meteor showers to known or suspected parent comets. Within such a stream, particle sizes span a wide range from micron-scale dust to centimetre-scale fragments. Smaller grains feel radiation pressure more strongly, which slightly reduces the effective gravitational pull of the Sun, on them shifting their orbits outward or inward depending on their initial conditions and size. Over long intervals, Poynting-Robertson drag an effect in which dust grains slowly lose orbital energy. As they absorb and re-emit sunlight causes them to spiral gradually toward the Sun. Larger fragments, less affected by these radiative influences, retain orbits closer to the original cometary path, altering only slowly under planetary perturbations. Together, these size-dependent processes ensure that the stream spreads in both space and time, turning an initially coherent trail into a more extended diffuse band of material. A quiet, poetic detail arises from this evolution. The dust left behind by a single comet can become part of the faint zodiacal cloud, a broad wedge-shaped glow visible from Earth's vicinity in dark skies before sunrise or after sunset. This glow, caused by sunlight scattered by interplanetary dust, represents the integrated contribution of countless grains from many comets and asteroids. Each particle is too small to see individually, yet together they create a subtle band of brightness along the ecliptic. In that glow, the phantom comet's dust, if it survives and migrates inward, joins an anonymous population, its origin no longer distinguishable. A once discrete nucleus thus dissolves into a general background, contributing quietly to a phenomenon that has been observed since long before its recorded apparition. A scientific mystery persists in the precise mapping between individual comets and meteoroid streams. For some showers, such as several well-known annual meteor events, correlations between stream orbits and known comets are strong. The timing, radiant position, and orbital parameters align, indicating a shared origin. For others, the associations are less clear. Some meteor showers lack an obvious parent. Some dust bands observed in infrared or zodiacal light measurements do not correspond neatly to known still-active objects. The phantom comet could in principle have seeded a stream whose signature blends with others, or whose present-day orbit has drifted away from the path that would reveal its connection. Without direct evidence, that link remains speculative, folded into the broader uncertainty of how many unseen or long-disintegrated comets have contributed to the dust environment. Soft ironies move through this domain of drifting grains. It takes only a brief period of vigorous outgassing near perihelion to release dust that will remain in solar orbit for tens of thousands of years, yet the active phase itself may last only weeks. It takes only tiny grains, each no larger than sand or smaller, to produce a meteor that briefly outshines every star in a patch of sky. Yet those grains originate from a nucleus that was itself barely visible as a faint blur. It takes only a narrow stream of meteoroids intersecting Earth's path to produce a meteor shower, recognizable every year, yet the parent nucleus that created the stream may no longer exist as a coherent object. As the meteoroid stream ages, planetary perturbations play an increasing role. Each time particles pass near a planet, especially a massive one such as Jupiter, their orbits can shift slightly. Some grains are deflected into new paths that no longer intersect the original trajectory. Others are shepherded into resonances where gravitational interactions with planets cause their orbital periods to maintain simple ratios with those of the perturbers. Over long intervals, these effects can compress or disperse portions of the stream, creating denser filaments and more diffuse wings. Observations of meteor showers from Earth confirm that some streams contain fine structure. Brief outbursts of high activity occur when Earth encounters a particularly dense clump of particles, while other years produce only a sparse display. A gentle modern analogy helps capture this behaviour. The stream resembles the wake of a ship on a calm sea. Immediately behind the vessel, the wake is narrow and bright with foam closely tracing the ship's path. Farther behind, waves spread, interact with currents, and gradually lose the sharp definition of their origin. Over time, the wake merges with the general texture of the sea. In the solar system, the ship corresponds to the comet, the wake to the dust and meteoroids, and the sea to the background of interplanetary space. The phantom comet, once the moving source, leaves a wake that gradually loses its direct association, even though its components continue to travel. More soft ironies appear when considering Earth's role. It takes only a thin crossing of a meteoroid stream for Earth's atmosphere to experience a meteor shower that recurs annually, timed precisely by the planet's orbit. Yet the density of particles within that stream may be so low that only a handful of grains actually enter the atmosphere at any given location. It takes only fragile dust grains easily crushed by hand, if they could be collected intact, to produce brilliant streaks that create the impression of violent fiery events. Yet the physical process is simply the rapid heating and ionization of air along a narrow path. It takes only the repeated crossing of the same stream over centuries for meteor showers to become part of atmospheric and observational records, while the original event that created the stream, perhaps a comet's disintegration, remains unobserved or poorly documented. As Poynting-Robertson drag continues its slow work, many of the smallest grains gradually spiral inward. They cross the orbits of the planets, sometimes encountering them, more often drifting past unnoticed. Eventually, some of these particles approach so close to the Sun that they are heated to sublimation or vaporization, removing them from the solid dust population. Others collide with fellow grains, fragmenting into even smaller pieces that respond more strongly to radiation, accelerating their inward drift. Over timescales far longer than those of human observation, the inner solar system's dust population represents a dynamic balance between input from comets and asteroids and removal by radiative and collisional processes. Into this balance, the phantom comet's material contributes briefly, then is redistributed beyond easy recognition. A scientific uncertainty lingers in the detailed lifetime of specific dust streams. While general timescales for Poynting-Robertson drag and collisional erosion can be estimated, the actual longevity of a particular stream depends on its initial mass particle size distribution and orbital configuration. Some streams may dissipate or merge with the background in tens of thousands of years. Others may persist far longer, their inner portions gradually thinning, while outer sections remain loosely bound. For the phantom comet, any debris it shed would follow this general pattern, without leaving a clearly traceable signature. The question of how long its dust remains a coherent stream is therefore left open, one more instance where physics provides ranges but not specifics without detailed initial conditions. Soft ironies return when the scale of time is considered. It takes only a brief human lifetime to observe multiple returns of a meteor shower, seeded by a long vanished source, yet the grains responsible may have been released before written histories in their present form. It takes only a few equations to describe the balance between radiation forces, gravity, and collisions. Yet the actual trajectory of any single dust grain remains practically unknowable once it enters the diffuse environment of interplanetary space. It takes only a few minutes of meteor activity on a clear night to remind observers of the presence of cometary debris, yet those minutes represent the ongoing consequence of processes that began with a comet's slow inward journey over millions of years. In the slow ambient arc of the narrative, the dust and meteoroid stream represent the comet's extended presence in the solar system after its visible form has faded. The nucleus may be gone or far away, the coma long dispersed, the tails invisible, yet the grains released during that brief active phase continue to orbit, collide, drift inward, and occasionally meet the atmospheres of planets. For the phantom comet, whose nucleus appears once in recorded observations, and then never again, this lingering residue becomes the most plausible enduring trace. It is not a sharply defined relic like a crater or a fragment housed in a collection, but a diffuse time-spread effect, a contribution to the subtle light of the zodiacal cloud to unremarked meteors and to the general dust that fills the space between worlds. From here, the story turns back toward Earth's perspective on such transient visitors, considering how historical records, modern surveys, and theoretical reconstructions attempt to link past apparitions, present meteors, and unseen debris into a coherent picture. The phantom comet, once a solitary entry in a list of observations, now stands as one example of how a single brief sighting can be related through slow, well-understood processes to a long, diffuse aftermath that continues regardless of whether any observer connects the two. Across centuries, the traces of comets accumulate not only in the sky, but also in records kept on paper stone, and in recent times, digital archives. Each record is small, a date, a rough position among constellations, a note on brightness or tail length, a short remark that a new star appears in the north, or that a fuzzy light drifts near some familiar pattern. These fragments scattered through chronicles, ship logs, observatory reports, and photographic plates form a faint paper analogue to the dust streams left in space. Scientifically, this archive provides the raw material for reconstructing the history of transient bodies. Astronomers compare old descriptions with modern orbital calculations, searching for links between meteors in present skies, comets long vanished, and dynamical models of how streams evolve. In this slow work, the phantom comet appears as one more entry, a set of positions and dates a brief mention, in a catalogue, a possibility that may or may not connect to other phenomena. One accepted fact underpins these efforts: the orbit of a meteoroid stream inferred from meteor trajectories recorded in the atmosphere can be compared with the orbit of a comet. When they match in inclination node and perihelion distance, a common origin becomes likely. Modern meteor radars and photographic networks measure the incoming paths of meteors with high precision, determining not only where they appear in the sky, but also their velocities. From these heliocentric orbits are reconstructed, revealing the stream's broader geometry. In parallel comet orbits, when known, are computed from telescopic observations. When these two sets of orbital elements align, a link between falling meteors and a parent comet emerges. For some showers, such matches are robust. For others, candidate parents remain uncertain or absent. A poetic detail lies in the way these correspondences unfold across time. A comet might have passed once centuries ago, leaving a trail of dust that Earth encounters every year. The original sighting occupies a few lines in an old observatory log written in fading ink, while the meteor shower it seeds paints brief, bright lines across the sky each time the planet crosses the stream. Archives preserve the quiet record. The atmosphere preserves the ongoing display. Between them, models trace invisible paths through space and time, linking a visitor seen under oil lamps or candles to meteors recorded today by digital cameras and sensitive detectors. Yet a scientific mystery persists in the attempt to connect specific ancient observations to modern streams. Many historical reports lack the precise positional data needed to determine exact orbits. Descriptions may place a comet near a bright star or in a particular constellation without enough detail to fix its motion. Meteor showers recorded in chronicles as star rains or celestial storms may reflect unusual activity within known streams or entirely different events. When modern researchers try to match these reports with computed times and radiance of showers, ambiguities arise. The phantom comet's brief, well-defined apparition belongs to a more recent observational era, yet even its orbit is uncertain. Any connection between it and present-day meteor activity remains speculative, one possibility among many in a large parameter space. Soft ironies thread through this archival landscape. It takes only a few carefully recorded meteor trajectories to define a stream's orbit with high accuracy, yet many centuries of observations passed with only qualitative descriptions of falling stars. It takes only a short paragraph in a logbook to anchor a comet's existence, yet the specific phrasing of that paragraph, choice of words, level of detail. Local weather notes may decide whether the record can be used in modern orbital reconstructions. It takes only a small difference in how an observer noted the position of a transient light to move a reconstructed orbit, enough that its connection to a stream appears strong or weak. The interplay between precise physical motion and imprecise human recording gently limits what can be known. In more recent times, photographic plates and digital surveys add another layer. Wide-field exposures capture the sky at specific dates, preserving the positions of stars' galaxies, and moving objects as small streaks or slightly displaced points. When a new meteor stream is identified, or when a lost comet is reanalyzed, researchers sometimes turn back to these archives, scanning old plates for unnoticed comets, or for early returns of streams. Occasionally, a faint smudge is found near where an orbit predicts the comet should have been allowing its path to be extended backward by decades. More often, the plates reveal nothing remarkable at those locations. For the phantom comet, any such retrospective search might find only empty starfields, reminding researchers that not every predicted position intersects a past exposure deep enough to reveal a faint visitor. A gentle analogy emerges here. The archive resembles a series of low-tide shorelines in which footprints and driftwood fragments appear and vanish. Each tide corresponds to an epoch of observations, each footprint to a recorded comet or meteor, each piece of driftwood to a dust stream crossing Earth's orbit. When the tide recedes, some marks remain, others have been washed away. Later explorers can reconstruct certain paths from what is left, but never all of them. The phantom comet's trail, both in space and in the archive, belongs to those partial traces clear enough to prove presence too incomplete to define the whole journey. More soft ironies arise in the interplay between models and records. It takes only a straightforward set of equations to integrate a comet's orbit backward and forward under planetary gravity, yet without accurate initial conditions, the integrated path quickly diverges from reality. It takes only a few meteor trajectories to provide a precise present-day stream orbit, yet linking that orbit to a specific ancient comet may require records that never existed or have since been lost. It takes only an assumption about how fast a stream spreads to estimate when its parent might have fragmented, yet that assumption rests on parameters that vary from one comet to another and are rarely measured directly. Theoretical clarity and observational uncertainty coexist, each highlighting the other. In addition, uncertainties in the non-gravitational forces on comets and in the early history of streams introduce further ambiguity. A stream today may no longer share exactly the same orbit as its parent once did, having drifted under planetary perturbations and radiative effects. For a parent that disintegrated long ago, no observational record may remain. In such cases, the stream represents a ghost of a ghost, a pattern of meteors pointing back to an absent nucleus, which itself might have been observed only briefly or not at all. The phantom comet fits naturally into this layering of absence. Its own orbit is uncertain. Any stream it might have produced would inherit that uncertainty, and then overlay it with dynamical evolution, complicating any attempt at identification. A further soft irony appears when comparing the durability of different records. It takes only a modest meteor stream to produce a shower occurring annually, potentially visible for thousands of years, while the written record of the shower's early appearances may last only as long as the materials and languages that preserve it. It takes only a fragile comet nucleus to release dust that endures in orbit for many tens of thousands of years. Yet the observational notes describing the parent may fade, be misplaced, or be overlooked in archives. It takes only a short-lived human tradition of skywatching to recognize these patterns, yet the physical processes that generate them continue regardless of whether they are noticed. Within this context, attempts to identify the phantom comet's legacy become a quiet exercise in bounded curiosity. Researchers can compare its recorded orbit with all its uncertainties to the orbits of known meteor streams. They can ask whether any stream's radiant and timing match what would be expected if the comet shed material along its path. They can examine whether any unexplained showers might align with a broad family of orbits consistent with the comet's limited data. The outcome of such comparisons may be negative, ambiguous, or suggestive, but not conclusive. In all cases, the physics remains steady. Dust spreads, orbits evolve, and meteors fall. The limitation lies in how much can be inferred from the small window of observation granted by history. In the ambient slow-motion narrative of the solar system, the records in the dark ancient chronicles, meteor logs, plate archives and digital catalogues form a human-scale counterpart to the dust and streams that persist in space. Each captures partial aspects of the same underlying processes: formation in distant cold, inward drift, outgassing, fragmentation, dust release, and orbital evolution. The phantom comet, seen once and then never again, demonstrates how these elements can intersect only briefly. For a short time, its physical presence in the sky and its numerical presence in records overlap. Afterward, its material continues silently, while its written trace remains fixed, awaiting comparison, reinterpretation, and quiet recognition that some correspondences, no matter how carefully sought, may never match exactly. In the broader architecture of the solar system, most small bodies travel on paths that loop back toward the Sun, repeating their circuits at intervals that range from months to millions of years. Planets follow nearly circular ellipses. Many asteroids trace modestly elongated orbits within belts. Numerous comets return with periods short enough that their reappearances can be watched and predicted across generations. Yet among this population of repeaters exists a quieter subset of passers-by, whose trajectories do not close. Their orbits are open, or so stretched that for all practical human purposes they may as well be. Scientific understanding accepts that some comets enter the inner system only once, either because they truly escape on hyperbolic paths, or because their bound orbits are so extended that their next perihelion lies far beyond any foreseeable epoch of observation. The phantom comet sits naturally within this conceptual space, a visitor whose first recorded passage is in operational terms also its last. In dynamical terms, a comet escapes when its total orbital energy relative to the Sun becomes positive. This can occur if the comet arrives from interstellar space already beyond the Sun's binding energy, or if it begins as a marginally bound Oort cloud body and gains a small energy increment during its passage through the planetary region. A close encounter with a giant planet can provide that increment, transferring orbital energy from the planet to the comet. As a result, the trajectory bends outward on a hyperbolic path never to return. Measurements of some comets show eccentricities slightly greater than unity consistent with such escape. Others display nearly parabolic fits that may conceal small positive energies within observational uncertainties. For the phantom comet, whose eccentricity is not known precisely, both scenarios remain viable, and the data do not force a decision between them. A quiet poetic detail lies at the boundary where bound and unbound paths diverge. The physical difference in speed near perihelion between a long-period bound orbit and a slightly hyperbolic one can be smaller than the uncertainty in its measurement, yet beyond the inner system, the two paths separate forever. One curve bends slowly back toward the Sun over millions of years, the other continues outward, joining the larger flow of interstellar motion. Seen in this light, the moment of closest approach that appears as a smooth, unremarkable sweep around the star carries in its fine structure the entire future classification of the comet a member of the solar system, or a traveller that merely passes through. A scientific mystery persists concerning the true fraction of comets that escape compared with those that remain bound on extremely long orbits. Models of Oort cloud dynamics and planetary encounters produce estimates, but direct observational confirmation is limited. The catalogue of known comets is incomplete, bias toward brighter and closer apparitions, and many orbits are based on short arcs. Some comets that appear hyperbolic may simply reflect measurement noise and unmodelled non-gravitational forces. Others that seem bound may in fact be heading outward on unrecognised escape trajectories. For the phantom comet, whose record is sparse, its placement in either category depends more on modelling assumptions than on decisive evidence. Soft ironies gather along this boundary of classification. It takes only a small statistical difference in velocity well below everyday human speeds to decide whether a comet stays within the Sun's influence or departs permanently, yet that difference may fall beneath the precision of current measurements. It takes only one close passage near a giant planet occurring in a matter of hours to alter the future trajectory over billions of years, yet no observation may record the encounter itself. It takes only a simple label in a catalogue long period nearly parabolic or hyperbolic to summarise that future, yet the underlying dynamical history remains far more complex than the label suggests. Another layer of soft irony emerges when considering timescales. From the standpoint of planetary climates, technological developments and human institutions, a comet, with a period of several million years, is effectively indistinguishable from one that escapes entirely. Neither will be observed again while continents hold their present shapes, or while current observing practices continue. Both appear once and then vanish from the record. In this sense, the distinction between bound and unbound is meaningful for the long-term structure of the solar system, but not for any practical aspect of observation. The phantom comet, regardless of its formal orbital energy, behaves in this human-centered frame as a one-time visitor. Beyond perihelion, the comet's trajectory carries it outward again. Its coma thins as sublimation slows and the tails shrink and fade. Activity subsides first in the innermost region near the nucleus, and then throughout the coma as gas production drops and dust disperses. At distances where sunlight no longer drives significant sublimation, the surface cools. If the nucleus remains intact, it re-enters a state akin to its pre-inward journey, dark, weakly illuminated and dormant. If it has fragmented, its pieces follow similar outward paths, each cooling in turn. In either case, the outward leg of the orbit mirrors the inward leg in shape, but not in visibility. The comet that approached as a bright apparition retreats as an increasingly faint, then invisible object, moving back into a domain where detection requires more sensitivity than is typically applied to the outer sky. Soft ironies continue along this receding path. It takes only small changes in heliocentric distance near perihelion to alter the comet's brightness dramatically, yet once it moves beyond a certain threshold, enormous additional distances produce little perceptible change from the standpoint of observability. It remains simply unseen. It takes only a modest nucleus to create a noticeable display when the geometry and distance are favourable, yet the same nucleus becomes practically indistinguishable from countless other small bodies once it returns to the outer darkness. It takes only days or weeks for a comet to brighten from invisibility to prominence, yet it can take years of outward travel for its activity to cease fully, and for it to return to a condition where time once again passes almost without effect. At greater distances beyond the region dominated by planetary interactions, the comet's fate depends on its total energy. If bound, it climbs to the farthest point of its orbit before falling inward again on timescales that dwarf human history. If unbound, it continues outward, gradually leaving the heliosphere. The solar wind slows and interacts with the interstellar medium at the boundary where the pressure of the sun's outflow balances that of the surrounding gas. The comet, now an inert fragment of dust and ice, crosses this boundary without any intrinsic change in its structure, moving from a region where the sun's magnetic and plasma environment dominates into one where the galactic medium provides the background conditions. The transition matters for the global structure of space plasmas, but leaves the nucleus itself largely unaffected. A final group of soft ironies settles here. It takes only a limited sphere of influence defined by the reach of the heliosphere to mark where the sun's direct plasma environment ends, yet the sun's gravitational pull extends far beyond that boundary. It takes only a small nucleus to traverse this frontier unnoticed, yet in doing so it carries away material that once resided in the sun's formative disk. It takes only a narrow interval near perihelion to generate all the observable phenomena by which the comet was known, yet the majority of its existence unfolds either in the deep outer regions of the solar system or in interstellar space where no direct observation records its presence. For observers and catalogues on Earth, the practical conclusion is straightforward. Some comets once seen are not expected to return within any meaningful planning horizon. Their orbits, whether formally bound with enormous periods or unbound and escaping, place their next potential apparitions beyond the limits of ongoing record-keeping. The phantom comet exemplifies this conclusion. Its brief appearance is preserved in tables and notes. Its future path, while governed by well-understood physics, unfolds mostly beyond the reach of direct measurement. In the slow, ambient narrative of the solar system, it becomes one among many small bodies that pass through the inner regions once, and then spend the rest of their existence in remote quiet orbits, either around the Sun at vast distances or around the galaxy itself. Over the full age of the solar system, comets pass through the inner regions in a pattern that resembles a slow, uneven rain spread across billions of years. Most of these bodies are never noticed from the surface of Earth. They travel on faint paths too distant, too brief, or too low in activity to draw attention. A smaller fraction become bright enough to enter recorded history, their comet and tails described in chronicles and measured in observatory logs. An even smaller subset appears only once in those records and then vanishes, leaving behind uncertain orbits and unconfirmed futures. The phantom comet belongs to this latter group. It is one example of how a single physical object can intersect human observation only in passing, even while obeying the same gravitational and thermodynamic principles that govern all bodies in the system. Scientific understanding places such comets within a longer context. Early in solar system history, during the heavy bombardment phases, large numbers of icy bodies from distant reservoirs likely bombarded the inner planets, delivering volatiles and shaping surfaces through impacts. Over time, the rate of such encounters decreased as reservoirs were depleted or stabilized. Long-period comets still arrive, but far less frequently than in those early epochs. Each one that appears now represents the continuing residue of that initial population. The phantom comet seen once and not again fits into this declining flux, one among many long-period objects whose rare passages trace the tale of a distribution that began when the planets were young and bombardments were common. A quiet poetic detail rests in the way these bodies connect distant regions and long time scales. An icy nucleus can begin in the deep cold of the Oort cloud, where the sun appears as a dim star falls slowly inward over millions of years, brighten briefly near perihelion release dust that becomes part of the inner system's meteoroid population, and then retreat again into darkness. In that sequence, a single small object links the outermost reaches of the solar system to the thin air of a planetary atmosphere, and links intervals measured in billions of years to moments measured in seconds when a meteor flares and fades. The phantom comet follows the same chain, even if its specific contributions remain unlabeled. A scientific mystery remains in how many such phantom comets have passed unrecorded. Before systematic telescopic surveys and wide-field detectors, many faint comets likely crossed the inner system unnoticed, or were seen only briefly without precise positional data. Even now, detection thresholds, survey cadences, and observational geometries limit what is seen. Models estimate the population of long-period comets that approach the Sun over given intervals, but the completeness of actual detections remains less than total. The phantom comet, with its short arc and uncertain orbit, may stand in for a much larger unseen population, hinting at a reservoir whose contents are only partially sampled. Soft ironies accumulate around this interplay between completeness and absence. It takes only a modest improvement in detector sensitivity to turn a formerly invisible comet into a measured object, yet many centuries of skywatching occurred with instruments far below that threshold. It takes only a few additional nights of observation to turn an uncertain orbit into a well-determined one, yet cloud-covered daylight or geometry can erase those opportunities entirely. It takes only one interval of technological progress to reveal that the sky contains far more transient objects than once suspected, yet the historical record cannot be retroactively filled. Comets like the phantom one retain their gaps. Another group of soft ironies emerges when considering Earth's longer history. It takes only a relatively small comet nucleus to create an impact capable of altering local or even regional environments, yet the vast majority of comets pass harmlessly through the inner system, interacting only with the solar wind and radiation. It takes only a sparse shower of dust grains from a meteoroid stream to create a meteor display that draws attention, yet the total mass of that stream may be negligible compared with the planet's atmosphere. It takes only one bright apparition to enter human myth art or scientific literature, yet countless equally real comets have visited without leaving more than a few lines in technical catalogues or no trail at all. In the present era, modern observatories, spacecraft and all-sky surveys continue to refine the picture. Sensitive detectors record faint comets at greater distances. Automated search algorithms identify moving objects in sequences of images. Space missions fly close to selected nuclei measuring composition, structure and activity in situ. These efforts turn some formerly abstract categories into detailed physical descriptions. Densities are measured, surface morphologies, mapped gas jets imaged. At the same time, the existence of objects like the phantom comet emphasizes that such detail cannot be obtained for every visitor. The framework of comet science relies on a combination of intensive study of a few examples and broader statistical treatment of many others whose data remain sparse. A final set of soft ironies settles in this balance. It takes only a small number of well-studied comets to establish general principles about nuclear activity and dust production, yet each individual comet still retains unique features that resist complete generalization. It takes only a single apparition of a phantom comet to confirm that such one-time visitors exist, yet the particularities of its orbit and internal structure remain beyond reach. It takes only a steady framework of gravitational and thermodynamic laws to describe all cometary behavior in principle, yet in practice, many specific histories of which this phantom is one remain only partly reconstructed. In the slow ambient perspective of deep time, the phantom comet stands as a representative of a wider pattern rather than an exception. It forms in the distant cold drifts inward under galactic and solar tides, awakens near the sun, releases dust and gas that merge with the inner system environment, and then moves outward again along a path that for observational purposes does not repeat. Its brief visibility connects the long timescales of orbital evolution with the short timescales of observation and record-keeping, leaving a trace in both the physical structure of the solar system and the accumulated notes of those who measure it. Long after the entry in a catalogue has been read, revised and archived, the body itself intact or dispersed continues its motion under the same quiet laws, part of a system that changes slowly and continuously whether watched or not. In the outer reaches of the solar system, beyond the orbits of the known planets, and beyond the tracks of most observed comets, small bodies continue to drift along elongated paths that change only gradually. Each one follows a curve set by gravity, shaped by ancient scattering events and distant tidal fields. Some of these bodies will never approach the sun closely enough to form comae or tails. Others will at some time in the deep future begin the long inward fall that transforms dormant ice into transient light. Most remain unrecorded, existing quietly in a space where time stretches far beyond human scales. Closer in the dust and fragments left behind by past comets, persist as thin extended structures. Streams cross planetary orbits at shallow angles, feeding occasional meteors into atmospheres. A cloud of finer dust produced by cumulative activity and slow erosion scatters sunlight into a soft glow along the plane of the ecliptic. Planets move through this diffuse environment steadily, their orbits nearly unchanged by the particles they encounter. The dust changes slowly under radiation and collisions, but the overall pattern endures a faint reminder of countless sublimation events and disintegrations that have already taken place. Around one planet with an atmosphere and a long tradition of observation instruments continue to watch the sky. Telescopes register new comets as moving points of light. Radar and optical systems track meteors as they burn in the upper air. Archives grow with each recorded event. Some comets are followed in detail, their orbits secured, their returns predicted. Others appear briefly and fade, leaving orbits that remain incomplete. Among these entries, the phantom comet holds its place as a single bounded passage, a set of coordinates that once matched a faint object and now point only to familiar stars. In the wider setting, nothing essential depends on whether a particular comet is seen again. The reservoirs in the distant dark continue to supply occasional visitors. The inner regions remain shaped by the combined influence of planets, dust, and light. The heliosphere maintains its flow outward into interstellar space. Individual comets form, drift, awaken, and disperse, each contributing small amounts of material and subtle changes to streams and clouds. The overall system evolves at a pace that blurs individual passages into a continuous background. The phantom comet, like many others, becomes one quiet element in that background, its brief appearance folded back into the long, slow motion of the solar system.